In this video, we're going to talk about a particular scenario in which we know that extension fields of a field are isomorphic. So let me just pose the following scenario. Suppose you have a field, f, and then you have some other field, f prime, which is isomorphic to it. And let's say we call that isomorphism phi, and let's assume that phi runs from f to f prime. Of course, we will use later the fact that there is also an isomorphism from f prime to f. That isomorphism is just phi inverse. All right. Now let's also suppose that we have an element u, and let's say that u belongs to an extension of f. So it doesn't belong to f itself. U is a root of an irreducible polynomial p of x belonging to the polynomial ring over f. Okay? So u is a root of an irreducible polynomial. Then that gives us an extension field f adjoin u. And let's suppose at the same time there is another element v. V is a root of the irreducible polynomial phi of p of x belonging to f prime adjoin x. Okay, wait a minute though. What does that mean, phi of p of x? Well, what I mean there is, let's say I've got some specific polynomial over here. Let's say 3 plus 4x plus 5x squared. So we're assuming f is something like the rationals. And you can actually verify that this polynomial is irreducible over the rationals. Okay, so what does phi of p of x mean? Well, I'm assuming that I have some map that takes elements of f to elements of f prime. And the coefficients of this polynomial do come from the field f, even though the roots might not. So what I'm going to do is I'm going to take this polynomial and map all of the coefficients through. I'm going to call those phi of 3, and then phi of 4, x, and then phi of 5, x squared. You'll notice here that I'm not putting the symbol phi on x. I'm not mapping x through phi or anything like that. That's because x is just a symbol that represents an indeterminate. It's not an element of f or of f prime. Okay, so that's what phi of p of x means. And one other thing you should probably be wondering about at this point is, wait a minute, if I map this irreducible polynomial through phi, do I always get an irreducible over here? And the answer is yes. So let me just write that down. This is like a whole bunch of tangential discussions here, but wait. Why is this irreducible? Well, if it were reducible, then I could write this polynomial phi of p of x as a product of two polynomials of smaller degree, which I could call q of x and r of x. And I realize it's kind of weird that I'm not putting phis on those as well, but I'm just assuming that q of x and r of x, those are polynomials belonging to the polynomial ring over f prime. Okay? So if that happens, then I claim that I could show that this original polynomial is also reducible, contradicting what we said about it earlier, that it's irreducible. Because I could then say the original p of x has to be equal to whatever I get by mapping q of x and r of x back through phi inverse. So phi inverse of q of x, phi inverse of r of x. Okay, and this would imply the original p of x is reducible, which is a contradiction. So that's why this other polynomial over here also has to be irreducible over f prime, which means that we get from this another field extension, f prime adjoin v. So what we're going to do is we're going to show that there is also an isomorphism between these. That there's an isomorphism which we will call phi tilde that maps f adjoin u to f prime adjoin v, and it's consistent with phi on f, meaning that it does to f exactly the same thing that phi does, and it maps u to v. We're going to do the actual proof of this theorem in the next video, but for now I just want to set the stage and talk a little bit about why we would care about such a theorem. Okay, so why do we care? Well, first of all, you should be wondering, when in the world are we going to deal with two fields that are isomorphic but not exactly the same field? Because the fields that we're used to working in are like the rationals and the reals. and the complex numbers. And there's not some other clever name for the rationals sitting out there somewhere. Like, there's not like the pseudo-rationals, and we need to think about extensions of the rationals over here and extensions of the pseudo-rationals over here. No, that's not the purpose of this theorem. What does happen, actually, pretty often, is we extend a field by adjoining a root of some irreducible polynomial, and then at the same time, we might extend that same base field by adjoining a different root of the same polynomial. And by this theorem, because there's nothing keeping me from taking this and this to be the same field, this theorem is going to tell me that those two extension fields are isomorphic to each other. So now we might think of another scenario in which those two isomorphic extensions now become these two base fields, and then we think about extending those further. So the whole end goal of all of this entire exercise here is to show that any two splitting fields of the same polynomial over the same base field are isomorphic. In other words, isomorphic, there we go. In other words, we're not going to get a different splitting field by starting with the base field and then extending roots, say, in some different order or something. This theorem will help us to show that no matter what we do, no matter how we get started, at every stage of the process of constructing a splitting field, the extensions that we're working in are going to be isomorphic to each other, which means that the fields we get at the end of the process, the splitting fields, will also be isomorphic to each other. And in fact, we can prove something slightly more general. If f and f prime are isomorphic fields, and p of x is just some polynomial in the polynomial ring over f, not necessarily irreducible, then the splitting field for p of x over f is going to be isomorphic to the splitting field for phi of p of x, where phi is an isomorphism between f and f prime, over f prime. So in other words, not only do we get the same splitting field by extending the same base field in two different ways for the same polynomial, but we will get the same or isomorphic splitting fields for corresponding polynomials into isomorphic fields. So in other words, splitting is kind of a natural process. It results in the same thing every time, doesn't depend on how we carry out the process, and that's kind of a good thing to know for where we're headed. So in the next video, we'll talk about how to prove this theorem, and then also how to prove that the splitting fields will be isomorphic as a result.